we'll make a start. Welcome to this week's seminar, everyone. This is the fourth of our seminar series, and again, I'll just remind you that these meetings are recorded, and I will post them to YouTube, hopefully in a much more timely manner. Just was editing this morning's one, actually, before we jumped on here. This week, we'll be going through some of the requirements for the next couple of weeks. We hope everyone has received replies to their email. Again, if you haven't, please remind us, ask us after this presentation. Make sure we get back to you, if not chased up with another email. Okay, so what we should be doing now is finalising our market research and costing plan that's due on Sunday, 31st of May. There appears to be a little bit of confusion on the time that it is due, but we'll clarify that in one of the announcements or let you know through the discussions. I'm not quite sure what the problem is, but we're fairly flexible on that as long as you get it in sometime on the 31st in your local time zone. That will do it nicely. Watch the discussion boards and teams for content. We've now covered all of the fundamentals of the project management, the things we needed to in the content. So now it's really individual project time. And if we jump to the next slide now, I'll go into that in a sec. Okay, first thing is congratulations on completing the videos. We have actually watched all of those. Check your YouTube page for the comments. If you had comments disabled, Savash would have sent those, the feedback to you via email. So make sure you've got a mark in the grade center that you've had a look at those comments because these will be used in the, or what you've covered in your presentations will actually be useful in the preparation of your final documents. This fortnight, please try and use your teams and the discussion boards for developing the prototype, getting some ideas from people with different backgrounds. Your market research and costing report is actually due, and think for these last or the second half of this program, who is the best person to be talking to you as an advisor, and try and get a little bit more direct contact with them. Okay, next, please, Sebash. The market research and costing plan, just a reminder of a breakdown there. It's 15% of your overall mark, so it is significant. It will also be used to a large extent within your final report, just modified to suit any changes that you've made in your prototyping. There's 25% on the industry analysis, so looking at what your industry requires, where the gaps are in industry, and those sort of areas. 10% on the competitor analysis. This is a critically important thing to know who you're going to be competing against. So a good investigation into who your competitors are, what your advantages are over them, etc. 30% on the products or services that you're providing. What are the advantages of it, how you're going to actually develop a system that will deliver these products or services. Your pricing strategy, 10%, again, crucial thing that you must keep in mind, otherwise you're either going to end up out of pocket or broke or worse. And finally, the SWOT analysis, which is 25%. Now, the SWOT analysis we covered previously briefly, but it is a crucially important thing and again will contribute to your final report. Most of the items in here you can take from the Canvanizer that you created first up. And if you've kept that as a living document, it will be very useful in developing not only the research and costing plan, but also the final report. Okay, this is the important part that I wanted to get to. Weeks 9 to 12 are very different from past moves. You'll only get out of it what you put into it because we don't have content there. The only thing we're really going to be doing is having these fortnightly meetings with you and discussing interesting topics to try and get conversations started. What we really aim to provide in this course is some expertise that you can ask to assist you in building, specifying your project and your development. And that's what it's really all about. It's making the contacts, it's working with your teams, it's working with your advisor, and that's where you will get value from the course. Sitting back and just coming to these every 2 weeks isn't a good use of your time and resources. we really do want you to contact us. We would like you to involve us in what you're developing. We find it really, really interesting, or we wouldn't be doing this. So make the best use of it. That's really what I want to get across. Question the advisors and try and stump us, because we don't know everything. If we don't know, we usually have a way of finding out. We have some fairly good contacts in other areas, which has come out already in the discussion on vibration sensors.
So this week and next week?
I'm just looking.
Oh, right.
Okay, it's not.
Sorry.
Okay, yep. This session, Sebastian's going to talk about sensors, signal conditioning, energy harvesting. Next week, I'm going to look more into how we construct prototypes and moving towards production. So we'll look at PCB manufacture, 3D printing, and lots of other interesting little things which are worth knowing as you move through the progression of developing prototypes and moving to manufacture. Thanks, Sebastian. Okay. Weeks 12 to 14 are actually not part of the course, but we need to keep the course open so that we can finalise the marking, ensure that students have achieved what they wanted out of the course, and a key one, help with any further developments. We don't mind doing this. In fact, we quite enjoy it. And from the previous run of the course, we're actually working with a few students. See if I can remember. One set in Canada, another lot in
Lebanon, one in Iraq.
Lebanon, and some other places. And we're continuing to work with them, and we hope that this will carry on through this program as well. So that's something we try and at least start establishing in the weeks that we're actually marking. So we will have presentations or these sort of seminars weeks 12 through 14 as well. Okay. So now I'll hand over to Sebash, who's going to give us a quick overview of sensors, and if his voice gives out, which I hope is not corona related, I'll take over.
All right. Good afternoon, everyone. Morning, evening. So I'm going to give you a very quick overview of sensors. I won't go too deep into the technical details, and I'd be happy to talk technical through email, but because we have business people here as well, I wanted to make the kind of the technical detail level on a particular level. So as a general rule, usually working with digital sensors comes down to this. You're getting a signal from that sensor, and that signal is going to be giving you a change in an electrical component. So a change in voltage, a change in current, a change in resistance, and a change in capacitance. Then you would get that data, look at the data sheet, and convert that to an actual physical characteristic. So these characteristics can be physical, chemical, and electrical, and we can have detectors that act as on and off switches for these signals. Now, these analog signals and these sensors, whether they're analog or digital, depending on what type of electrical component they're measuring and what type of change they're presenting to us, are connected to two main categories. We have active sensors and passive sensors. With active sensors, they generate a signal that's normally either a change in current or voltage, and they respond to environment stimulation. Examples of them are thermocouples, piezoelectric sensors, and accelerometers. The magnitude of the generated signal is usually quite small, so we need to amplify their magnitude so we can read them and apply data processing methods on them. More on that a bit later. So we also have passive sensors, and these are the types of sensors that typically give you a change in resistance, capacitance, or in inductance. Examples of that are thermoresistors, thermistors, capacity, and humidity. Again, as far as we are concerned about the type of data that they're giving us, again, at the end of the day, it's usually that electrical component characteristic, the change in that component that they are giving us, and we're looking at a data sheet and converting that to a realistic real life characteristic. In a few slides, I'll show you a couple of examples of these changes and how you can go from that raw reading to an actual, say, temperature or pressure and so on. So with the first example, this is a very popular sensor that we use here. This is called an FSR, force sensitive resistor, what it is, it's basically when you apply pressure in it, the resistance that it produces changes. So here's a very simple circuit for it and a very simple Arduino code for it. We basically initialize the pin that's connected to one of the sides of the resistor, and the other side it gets connected to the ground, and we can just do an analog read on the pin that's connected to our Arduino. Another very kind of popular sensor, TMP36. This is a temperature sensor, and this is a very good example of if you hear the word raw data from a sensor, it's raw data because it's at the stage before any processing has been done on the sensor data, or any filtering, or any conversion to a real life characteristic. So here, the actual value we're reading is a change in voltage, and then we pass it to this equation to convert that to an actual temperature in centigrade. So the connection of this one is fairly simple. You have 3 pins. One of them gets connected to your ground. One of them gets connected to an input voltage, and then the third pin, which is a signal pin, you connect that to one of the pins of your microcontroller. We do an analog read on that pin, and we monitor the changes of that, as we can see in this example code here. Now, if we ignore all of the comments here, it's pretty simple. We initialize the pin. We start our serial monitor, which is where we are passing the information through. We are reading the pin that's connected to that signal pin of the sensor, and over here at the bottom, we are converting that reading to an actual temperature. And another line that I've put in here, converting that temperature to a Fahrenheit from centigrade. Another very useful sensor that Ian and I use a lot in our research are IMUs. So IMUs are inertial measurement units, and they're basically an accelerometer, a magnetometer, and gyroscope built on the same chip, or sometimes on the same PCB. And they have very useful and interesting use cases. We use them in lots of projects like monitoring movement of a wheelchair. We use them in monitoring Widekind movement for people who have a visual impairment. I'll show you the examples of those in a bit. But a very interesting thing about IMU sensors is they're cheap, but using them and basically having the sensor, having some sort of a microcontroller and a transmission device, we can capture movement and we can capture motion, especially if the movement that you're monitoring is, say, in terms of human movement, we're looking at the joint movement. It's not going to be as accurate as the, say, multi-million-dollar motion analysis lab, but it's going to be accurate enough for the purpose of, say, occupational therapy and helping people get those treatments and specific movements that we want to monitor, which can be done in a device that can cost less than, say, $200. So that's why they're very useful. So within there, we have the accelerometer, and it measures the linear acceleration in 3 dimensions. They're also regarded as gravity sensors, as the readings are equivalent to gravitational measurements when the sensor is static or under low speed of movement. And we use trigonometric algorithm to convert the values that we're reading from these IMU sensors and accelerometers to movement. And here's an example of calculating the net acceleration in a particular direction. We also have some more on that diagram. Can also get the angle with this one, which gives you the acceleration measurement from each of the axes that we're looking at. We also have the gyroscope in there. The main purpose of that is for maintaining or measuring orientation. So usually accelerometer and the gyroscope in an IMU are used together, and we have different orientation techniques to use the data from both of these sensors within the IMU to get our general orientation frame. We do have magnetometer in there as well, but because it's prone to electromagnetic interference from the environment, I think Ian mentioned something this morning about even a file cabinet next to the sensor can mess up the accuracy of the data. Was that?
Any metallic object will affect the magnetometer. So we haven't actually found them to be of much use, except we're now looking at using them for an initial position. So we can use a distortion from the magnetic field to work out where the position of a sensor is. But as a compass, as a direction heading, not too much luck so far.
And if you're interested in using IMUs, because I have a lot of experience with them, send us an email through that IoT capstone, and I have a handy, I've called it the IoT links, it's an IMU links file, and I can send those links to you, so that can help you get started in getting data, converting that data to movement, acceleration, angular velocity, and then finally processing using accelerometer and the gyroscope to get an orientation frame through MATLAB. So if that's something that interests you, let me know. So here are just examples of equations we can use with the gyroscope to measure angular velocity here. Now, when we're talking about sensors, the other topic that comes into mind is signal conditioning. Usually, especially with IMUs, the raw signal that you're getting from your sensors isn't clear enough. It might require linearization, amplification, or filtering. The examples of these concepts you can see here. So linearization is if we have a non-linear sensor, but we wanted to see the response in a linear fashion, that's where we would apply linearization. Amplification, as we mentioned, in the case of some sensors that would require amplification for us to be able to read them and process them better in the future. So we can monitor the changes that they're representing clearly. And filtering, which is a kind of a bigger area in its own right, especially with IMUs, because after you're using them for a bit, you can see that the signal is going to drift. And I have a couple of the drift examples later on. So whether you're handling the drift while you're capturing the data, or it's something that you correct after the data has been already captured and you're correcting that in post-processing, depending on the processing power of your current microcontroller that you're using, it's its own topic, and that's what I'm focusing on for my own PhD research. So a couple of IoT type projects that are going on with IMU here at Curtin. This one is something that actually my wife's working on with Ian and David. So this is an early prototype. It's an IMU sensor connected to an Arduino Pro Mini and a Bluetooth transfer module and a battery that's connected to one of those sensors to a wide cane and the other one to one of the legs. And the idea was this was designed to remotely train a visually impaired person who's working at who's living in a remote area to learn how to use the wide cane. So the movement of the wide cane and the legs can be monitored through here. Now, an interesting thing about this is, and this is something that my wife's actually looking into writing a paper on, as you can see, there's only one sensor connected to one of the legs. We're not monitoring both of the legs because by the correlation we can get from one leg and the wide cane, we can tell where the second leg would be, so we can reduce down the number of sensors, so we are dealing with fewer data, and that's going to save time on our post-processing. Another one that I'm working on, so the same idea, IMU sensor, microcontroller, and this one is an RF transceiver. This is one of our early prototypes. So I'm using these sensors for specifically looking at joint movement on the wrist. And this is specifically for children with cerebral palsy. So I have two of these sensors, one connected to the back of the hand, one slightly above the wrist. And using the data from these two sensors, we capture that joint movement. Again, I like this picture because I've termed it my sticky taped prototype, as it's literally the sticky taped piece Arduino board to a transceiver. And the point I wanted to get across, and this is something Ian is going to focus more on his presentation next week, is when you're starting out, you are working with these development boards, you're you're working with wires and these big boards to get to a prototype proof of concept. And then the next step from that is where you would, I'll have it in a few slides, where you would go from there, take that design, now that it works as a proof of concept, now design a PCB for it, now design a casing for it, make it an actual product. What I have here, I want to show you an example of one of my data capturing sessions. This is me just sending that data from my IMUs to the receiver station. And I have a sensor ID because I had two sensors. This is just one of them at the moment. And then reading the data from the accelerometer and the gyroscope. And later on, I capture this data, process it through MATLAB, and then run machine learning algorithms to determine whether a movement is falling the range of cerebral palsy or not. So we can have hopefully prevent someone or start occupational therapy as early as possible within a certain degree of accuracy. And here you can see a comparison between data collection session. This was, we had asked the people who were being tested to do a simple stop motion, a stop sign motion with their hands. And as you can see on the left-hand side, which is the abnormal data, on the right-hand side, which is the normal data, you can see the maximum angle for the peak of the diagram. Comparing them, you can clearly show which one had the limited range. So the right-hand one is, I think it's about 90, and with the left-hand one, because cerebral palsy is something that can affect the range of movement, the peak is about 25 degrees. Another example I wanted to show you, so you can see that those drift problems and the type of interpretations we can have from a sensor, even without doing filtering. This is a quick test I was running to determine what's the maximum range for an acceleration in terms of G that we can reach when I'm constantly moving my hands. So slowly moving the hand, then moving slightly faster. This was a small issue we were running into when we captured some data, and when we got it, we saw that there was a cutoff in the data. So when we got the sensors back in, it turned out that the scale that we had set for the accelerometer was set at 2G. But the movement, even a very simple handshake, would have reached above those values. So we had to change the scale back up. Now, here, especially on the z-axis, and as I said, this is before the data was processed, and this is from a commercial sensor, not the ones I showed you. As you can see, it has drifted down a lot. So this is a very good point in showing you why it's important to look at those signal conditioning once you have all of your setup, just to make sure the data you're getting is not being drifted like this. So we can always, this is something that we can always fix in post, and then once we have that fix in place, hopefully by having a more powerful processor, and we can start doing some of that pre-processing while we're capturing the data, so we don't have to fix it as much as a post-processing implementation. And
quick jump in here, Savash. One of the key things to take away from this is the fact that sensors are not nice, perfect devices. So we need to look at the signal conditioning and linearization in a critical manner. Most sensors will not give you a straight line reaction or a linear relationship to what they're sensing. There will be some curve or some sensitivity, might be light sensitivity, or could be temperature sensitive, things that will make our line, instead of being nice and straight, where we can say at this point it matches 30 degrees C, it'll actually be more of a curve. So you'll get a more rapid change at higher temperatures, for example, than you do at lower temperatures. So one of the things you have to be able to do, and this is normally done and published through the data sheets, is apply a formula to the raw readings that you're getting to linearize the output. The other part, again, to take from this is the need for signal conditioning, the removal of noise. In IMUs, that's really difficult. Part of the noise is drift, but in a lot of other types of sensors, you're reading either harmonics, which is a multiple of the frequency that you would normally get, or there are stray elements like electromagnetic radiation that's being induced into it, and you want to find out only the data you need, not the noises induced. So you need to have a method of working out what is actual data, what is noise, and how can I subtract that noise from the sensor. Otherwise, you'll be collecting lots and lots of data which has absolutely no meaning. So linearization and noise and signal filtering are critical components, whatever sensor you're selecting.
Thank you, Ian. So now, remembering back from that sticky tape prototype, this is something that I'm working on at the moment, and it's fun enough. It has been kind of halted back because of the COVID-19 pandemic and all of the kind of manufacturing having stopped over at China. But the idea is you would eventually get from, rather than having a bunch of stuff sticky tape together, to designing your own PCB, which you would have all of your sensors and circuitry embedded on the same PCB as a single device, which would get it closer to an actual prototype, to an actual product, and that you can eventually get to the market. Now, another sort of idea I wanted to introduce you guys is looking at these sensor packages and development kits that have become popular in the past couple of years. These packages, they offer you an open hardware, open software package with a microcontroller and a bunch of sensors built in on the same small kind of form factor, and they usually offer a phone app for it. And the idea is you would use these devices to play around and prototype devices around sensors if you don't have that much of an experience. So they're not that expensive. They can get to like a $50, $40 range. But the idea is you would start with these, and then because they offer their PCB design as open hardware, you can take that design, remove all of the other sensors that you're not using. It's not that straightforward as I'm making it, but it makes the starting point a bit easier. And then design your own sensor tag. And the one I showed you is based on another example of these, which I'll show you in a second. And because they offer that software component for you as well, so you can get to a working prototype a bit faster. So this one is a SimpleLink sensor tag by Texas Instrument. And as you can see, it has a bunch of sensors. It has a pressure sensor, light sensor, humidity sensor. It has an IMU N9251. It has a PCB antenna. Here's a closer look at it. And sorry, the picture is a bit blurry, but this is a look at the interface for the phone app, where you can choose between the multiple sensors and have multiples of them on or off at the same time and get a real-time reading of those sensors. This is what my that PCB prototype I showed you is based on. This is called the Nordic 52 Thingy, and this is by Nordic, and they have lots of. This one has a lot more sensors on it, and it has a speaker and an LED that you can change through the app. And they have better documentation compared to the sensor tag in terms of what you have available to you, and in terms of them providing the PCB layout of the board itself. So this is an interesting kind of little product to play around with if you're interested in working with sensors. And again, these are offered as a development products. So they're offered in such a way that you can develop for them, write your own code for them, play around with the different sensors that are on the board, and get a first experience with sensors and working with sensors. Because it might be a bit more difficult starting right off with, say, an Arduino connected to a sensor through wires. So this way you don't have to worry about that part of it, and you can just start looking at the sensor data itself and looking at how that data can be interpreted and processed, if that's something that interests you more compared to building that low-level component of it. And here's a look at the interface for Nordic Semi. And this picture at the top, they actually have a 3D model of the sensors. When you move the board around, you can see that 3D model moving around, which is it doesn't work very well. It loses calibration very fast, but it works okay enough that you can start building some prototypes with it. And so the last topic I wanted to cover is is energy scavenging. I think I skipped 2 slides, sorry. And the idea of using the environment around you to power your IoT devices. And this is going to make your device very eco-friendly. You're potentially saving cost and saving battery life and the overall cost of the device as well. The main types.
I'll throw one other thing in there if you like, Samesh. One of the key things with energy harvesting is even with extremely low power usage, at some point your batteries are going to fail. And particularly in industrial systems, you don't want people having to run around and change batteries, even if it's every couple of years. So the idea of using energy harvesting to provide, well, what's basically perpetual energy is very, very attractive in low power IoT devices because of the maintenance aspect. There's all the green benefits as well, but it's for most industries, it's the maintenance saving.
Yeah, thank you. That's a very good point, Ian. And so examples of energy harvesting with solar power, wind power, human motion, and radio frequency. And we'll show you examples of those in a bit. So the existing energy harvesters like photovoltaic cells for solar power, wind turbines for wind power, piezoelectric cantilevers for vibration, and electromagnetic generators for radio frequency energy or RF energy. So with solar energy, we're starting to see a lot more of them here in Australia with solar panel with all these different shapes and sizes on people's rooftops. And there are many things that can affect solar power in terms of how much shadow affects the amount of power you're getting from these solar panels, and depending on the size, how much power they're actually able to provide.
Back to the solar. I'm sorry to keep interrupting you. It's just these things spring into my head and I can't stop talking. Solar's a great issue. It's really, really cheap nowadays. Look at all of the LED solar lamps that you can have in your garden, and they last a while before the batteries die. However, in a lot of instances, solar power is not an option. If we think in the outdoors, we've got one particular project which is measuring something in houses' front yards, and you can't use solar power there because people like me will grow rose bushes and trees, fruit trees and things in their garden, which will shade the solar panel. So in a lot of instances, the installation site rules out the use of solar energy. So keep that in mind when you're designing. Think where it's going to be placed. Are you actually going to get a reasonable amount of sunlight on it?
And the next one, wind energy, which is harvesting it's a relatively mature technology with wind farms and which are now connected to the grid. We have large wind farms, for example, the one near Stockton is CA that contain about 5,000 modern wind turbines. The availability of wind energy is less predictable than solar energy, and not all of the wind power can be captured because of the conversion techniques that are being used there. And the efficiency of the wind turbine depends on the actual speed of the wind. So the placement of them is very important. Anything you want to add here, Ian?
Being mechanical, they're also relatively expensive. Anything mechanical is expensive.
Definitely. Kinetic energy, this is an interesting one, and I found a very interesting little hobbies type project on this, which use kinetic energy like vibration and harvest that by micro power generators, and they can become power sources for fitness and wristband, wireless sensors, other portable applications. They tend to use piezoelectric, electromagnetic, and electrostatic mechanisms for generating them. They're low frequency, so human, and because of the low frequency of these devices, they're very sufficient for small appliances, which can be perfect for us for smaller IoT implementation, depending on where they are placed. And the last one, radio frequency, which is the energy that is broadcasted from millions and billions of radio transmissions, including mobile phone, portable radios, mobile base station, and broadcast stations. This energy harvesting is poised to serve as an energy source to low power devices, which makes the product more stable and reliable and eco-friendly. It supplies to various kinds of wireless sensing nodes with 24-hour operation, and energy transmitted from these RF sources can be very high, up to 30 watts to 100 gigahertz, but only a small amount of that can be scavenged in real environments, and the rest is dissipated through heat and absorbed by other materials. Anything, Ian, here you can think of adding?
Just a classic one from many, many years ago. Tesla actually wanted to have wireless power, which works along the same principle. So he tried to transmit power wirelessly, and that's where we get things like Tesla coils from. So yeah, it's possible, but it's not terribly efficient.
Definitely.
Mind you, in sensors, if they're located close to sources of energy such as mains power, the power transformers, power lines, you can actually harvest quite a significant amount of memory from those environments. However, you are stealing from the electric company, so it's a big no-no generally.
Definitely. Ian, do you want to take this one, the vibration?
Yeah, sure.
energy?
This particular one, the electrostatic conversion of vibration, it's purely experimental, and it basically works by the vibration moving the weights, which are silicon weights, and they create static electricity on a capacitive device. So if you know how a capacitor works, it stores a charge by building up, how do we put this very simply? It builds up a static charge on one side of the capacitor, which then attracts electrons to the other, and that holds a charge. That's basically what static electricity is, very roughly speaking. And by having the static electricity generated between the glass and the variable capacitance semiconductor in the silicon, you can then turn this device into what is basically a capacitor and charge it up through the vibration and the static electricity generated there.
The second one, the rope-driven wideband piezoelectric vibration, which is based on the tension of the rope and a bunch of weight connected to there. We actually had another student graduate with a similar idea to that, where he had weights connected, and the other end was connected to a simple DC motor. It was more a proof of concept, but the idea was when the weights would pull down the rope, they would cause a reverse rotation on the DC motor, and then that would cause it to hold a charge. And he was using that as kind of a portable battery. Well, in his research, it turned out that it wasn't really feasible unless the scale of the product was very big. But this is another example of kind of using that rope-driven piezoelectric vibration for energy harvesting.
I'm not 100% certain on this, and I might actually have a bit of a look. This is how the quartz self-winding watches work. So there's a little wheel in there that spins around, moves back and forward, and that pulls up and down on the piezoelectric strip, which generates the voltage that's required.
I see. And this one, this was
actually, I just found it.
Oh, interesting.
Wikipedia answered it for me.
This one is a piezoelectric shoe, and the idea was there was let me just give full credit. It was by a guy called Abel Hines. So he was going running every morning, and apparently he had an older iPhone, and he was constantly running out of battery. So he ended up putting a bunch of piezoelectric sensors as a shoe inlay, and you can see him on this left picture scavenging a component of an old light bulb, and he used that inlay. So when he was going running in the morning and connecting that to his phone, to use that that kinetic motion to generate power and power up his phone, which I thought was an interesting project. If you search his name, he has a big blog about it, and he goes through the steps of how he managed to build this kind of prototype here. And of course, another old popular one are hydroelectric generators. which are the basic structure for them, can be seen here. Ian and I have been recently looking into working on an RAC project with RAC, which is an insurance company here in Perth, Australia. They were looking at implementing a method in water valves so they can prevent catastrophic kind of pipe bursting from happening, because that's a big cost for insurance companies. Because if that happens and someone claims water damage, they usually have to take the whole family, put them at a hotel or a suite while their property is being kind of renovated, kind of being fixed and repaired. So that adds a lot of cost. So they come up with an idea of how about they get into this market themselves. It's interesting for an insurance company to be looking at prevention. And so as a part of that, we were looking at if we are monitoring for our flow meters that we're going to put in there. So because we are thinking of looking at the flow of water as a way of determining that catastrophic event happening. And we saw a couple of these water turbine generators that work on the same principle of those bigger hydraulic ones that use the flow of water to generate power. So this one, this produces a 5-volt DC power, which can be pretty much enough for a small IoT solution. Another one I found, this one, I think I found this one on Amazon. This one can get to up to 12 volts. And this one, which I think it started from as a Kickstarter project, and it seems to be fairly popular in the States. And the idea is for people who they're marketing it as a camping kind of accessory, where you would go camping and use this to charge your phone and iPads. Because I guess, God forbid, we go a day without using our phones. So I guess an interesting market. And Ian, I think you mentioned another use case for these devices for
water. It's an ancient technique, as we all know, but it has a great deal of application, particularly in, say, rural agriculture. Not these smaller ones, but having a larger water wheel driving or supplying the power to an IoT solution in remote areas is something that's sort of gaining popularity because it can be done relatively cheaply, and water generally keeps flowing, except in Australia where we have lots of droughts. And it's definitely, as I said, gaining in popularity as a way of powering systems in remote locations. There's lots of images of how to do this and examples available on the net if you're interested in this side of things.
Okay, I think that's all we wanted to cover for today. We'll get to questions, and in the meantime, once we got to the questions, I'll try to show you where I would typically go to get information if I face a new sensor, and how I would go about getting source code and example code for it. So feel free to ask any questions. Ian just popped the link in the chat.
One of the things that came up this morning is a person was looking for industrial type vibration sensors, which actually are quite expensive. If you don't want to at this point, and we'll get to you Matthew in just a moment, if you don't want to do that, there are ways of finding data sets of existing sensor data, and this is just one of the links. NASA has another one, and rather than buying a very expensive sensor to test on your prototype, you can download the data file and then have something like a baby Arduino Nano Micro outputting that data set and acting as an emulated, which is different to simulated, an emulated sensor. And that is a good way of just shortcutting the design process and saving some money initially. So you can get your sensor looking like it's working, do the smart part on processing that data and filtering the data prior to actually having to invest in that particular sensor.
Matzi has his hand up.
Oh, yeah. Hello, thank you. So my question is related to the sticky boards with sticky tapes and also with the sensor and if I develop. So I understand and I saw it already. So to have development boards is quite easy. But now where I do not find that much information that would be very interesting for me. So assuming we have, or I have developed a board with the sensors and all what I have, and I have theoretically a final prototype. So what is then a typical way with going from this development board to, let's say, a small batch production or something like this? Is then the partner more that one that is developing also or offers these development boards, or are there special industry companies, or how it's flowing, let's say like this?
Yeah, we're actually running through that next fortnight. But beforehand, you could have a look at the recording from the last run of the Capstone project. But in general, if you've designed the PCB, you can upload the the PCB format file.
Gerber file?
Yeah.
Okay, Gerber.
The Gerber file to many companies, mostly in China, Hong Kong, Taiwan, that will manufacture a small run for you at an unbelievably low cost. About 6 months ago, we had a set of PCBs made, and they normally sell it by the area it's going to take up. So PCB material comes in a 300mm by 300mm sheet as one of the sizes, and it will cost you the same as to get one device made as to fill the entire sheet, because it's the same time to them. And I think we got 9 or 11 of these devices made for a grand total of, again, from memory, was it $9 US?
What? Okay.
It cost over $30 to have it shipped out to us.
Okay.
The cost of the manufacture of the boards is infinitesimally small. They will also populate it as well. So if I put all the components on for you, they have very good buying power, so the cost of the components is low. The cost of assembling it is also very low, and it becomes lower and lower the more you do. The only problem, and I keep raising this, is be very aware of quality. This manufacture is fast, cheap, or pick any two. So we have had problems in the past, but because it is so cheap, if you have a proper testing regime in place, you can accept these 30% failures that you'll end up with. If we look at Australian manufacture, it was going to cost us for the same amount of boards, setup cost, $200 or $300 to produce them, and then the components on top. We're looking probably a couple of $1,000 investment just to get our first prototypes, compared to $40 in China. You can buy a lot of $40 batches for the couple of $1,000 it costs to produce a high quality board locally. But again, it depends on market. If you're working in a medical field, you would want the high quality no matter what the cost. The prototyping, China's fine, but just be aware that you will get failures.
Some of the ones, as Ian mentioned, we're definitely going to cover them next time around, but I think one of the ones that I think we used before, PCBWay is one of them, and some of them also offer design evaluation. So if you have a design and you want them to test it before actually building it, some of them do offer that services. So
look at these prices down here: 100mm by 100mm board, 10 pieces cost you $5.
And another thing I want to show you guys. This is how I typically go looking for information for a particular sensor. I look at some of the popular manufacturers like a SparkFun, DigiRobot, and if you have any local kind of electronic shops that have websites, with these products, they usually offer hookup guides and detailed tutorials. So, for example, this is for the IMU sensors that I'm working on. If we look at the lookup guide that they have on their website, they give you, I would say, like a more simplified version of the data sheet with the details you would need for you to get started working with these sensors and actuators. So, for example, with this specific one, they show you how you can hook it up to an Arduino, how you can program the Arduino separately, what sort of headers you can use to solder and connect it. And of course, they offer sample codes for starting to get data from the sensor. So then you can go and modify that code for your own project. So my suggestion would be first go to these sorts of websites, not to get the actual sensor from them, but to get their information. And then you can probably find a product similar to that from like a local store or something. If you have like a electronics store in your country that you can save on shipping, well, you can use those. So it's a good idea to start there. This is where I would get my information. So this one, again, as I said, this one, DigiRobo, DigiKey, Altronics. Altronics doesn't have that much information. There's one, Core Electronics isn't a bad one. Just a couple of examples of the kind of shops that do offer these sort of tutorials from the PCB manufacturers and sensor manufacturers that you can use in your projects to get started and get to sample code. Because it might be a bit jarring just to go on GitHub and get their source code, but this way they come with a more descriptive kind of introduction of the sensor. So I think it makes it a bit easier to get started working on those on these types of projects. Anyone else? Any questions?
Yep, Amina. Yeah, and Sherry came in second. So Amina first.
Hello. I have a question related to the market research. When I've done the market research locally here, I find something a bit difficult to find all the market shares for my competitors. They are not providing informations, and some of them, like NGOs, they work individuals, and they are not really have like companies, just like funding from other, partners or whatever. So it's kind of hard to find the market share. So should I expand my market, like not just locally? I find it a bit hard to find all the information here. Unfortunately, they are not providing all the informations. So should I expand? Should I like Middle East or North Africa, for example? Maybe be a bit like I can work there. I find myself there. So what do you suggest?
Yeah, I would definitely expand out to any market that is similar to yours. What is your IoT product again?
It's a smart sanitizer gate.
Sorry, what was that? I didn't.
They have a smart sanitizer gate so people would pass through and then get sanitized for COVID-19.
It's a whole system, not about this. It's not about the sensors. It's all the system, like monitoring all the system. Yeah.
Well, that's really applicable.
And surface.
That's applicable pretty much anywhere. I'd look for other areas that have similar demographics, similar population densities, and get information from them. It's going to be very common given the population environment wherever you are. So again, I'm not sure where you are, but if it was in Australia, I'd be looking at anywhere in Europe, New Zealand, North America. They would be the same sort of markets.
Yeah, North Africa, Libya, and that's why I found it its potential to do this in my market here, because I see its big potential to find this market, because there's not a lot of competitor about this product here.
No,
you know what I mean?
Yeah, I do. I would definitely be looking outside of the Middle East, even towards more populous countries like India, Sri Lanka. I know they've done some work on this in Sri Lanka and India. probably not China because they wouldn't tell you anything anyway. But yeah, looking for, limited resource countries,
Okay.
mid to high density populations,
Okay, sure.
fairly crowded cities, and that would still be applicable.
Yeah.
Shoot us a line offline if you like, with a reminder to see if we can find anything else.
Yeah.
Is
I
that
think
okay?
I think Sherry was next.
I'm having troubles with the competitor analysis also. I've been able to identify one major competitor that pretty much provides many of the services that I would, just more expensive. But as far as being competitive with the product, there's other smaller companies that do like one feature of what I'm instead of the whole package.
You're very quiet, I'm afraid.
Pardon?
You were very quiet.
Is this any better?
Yep.
Okay. So there's the one competitor that's a major competitor, but as far as any of their market share, I find a 1 to 5 million US dollars is what their projected income is. I can't find any tax filings for them to say what their actual income is. So finding out what their market share is, I probably spent 15 hours trying to find just that item. So I suppose I'm
Okay.
looking for help on how to do this. And the metric is I have to have 3 or 4 competitors, but I can only find one primary competitor, and I can find several smaller ones, but they are typically out of China, Taiwan, Hong Kong. So I'm not going to get any information there.
Right. That's again not a problem. That's more of a guide for general devices. If you're looking at anything in the niche market, you're going to find it very difficult to find out who your competitors are, what they're up to, how much they're earning. And it just needs an explanation of that. And then look for using your market research, not the competitors part. Who wants your product? How many people want your product? Is there room for multiple vendors? And approach it from that way.
Would you mind reminding us what your topic was, Sherry?
It's an aquarium monitor,
Oh,
so
yes.
that it'll do low and high levels, and then automatic refill. It'll detect leaks. So
I think your
I'm able
market
to
analysis
find
is
smaller. Sorry.
Yeah, I think with your market analysis, you look at you should be able to find out guesstimations on the number of fish owners or fish enthusiasts that exist. So the way you could do that is rather obscure, but perhaps if you looked at the magazines that are published in the home aquarium market, they will always publish their subscription readership levels, because that's how advertisers decide whether to advertise with them or not. And if you find that in, say, North America, there are 20 million subscribers to this magazine, you have a 20 million household market for your product, and infer it from that sort of information. And the fact that you haven't got easily identifiable competitors isn't a bad thing. That's a really good thing. Does that sort of
I
make
was
sense
just
to you?
looking at the metric,
Yeah,
3 to
no,
4.
we will keep that in mind. If you don't have competitors, you can't do a competitor analysis.
Right.
So if there is only one large competitor, well, make sure you can find as much as you can about them, but then look more at the market size. If you were doing something at the opposite end of the scale, where you were creating an IoT device with an extremely limited market, and there were quite a few competitors, it'd be justifiable to say you shouldn't really go ahead with it. However, if you're going for that same niche market and you can't find anyone who's doing it, you can't do a competitor analysis, but you can use the market analysis as the justification for the lack of competitor analysis.
I have just a question also about the market research. As I was trying to get the pricing from the competitors, like I sent them for quotations, but they didn't. I do the smart recycling bin solution, and I found like a couple of two companies that do a similar thing, but not a full solution. But when I tried to get the prices from them to understand how they do price their product, I didn't get still a reply from them, and I think I will be running late out of the date of the market research uploading. So if we couldn't really get a pricing of our competitors, can we just like rely on something else while doing this?
You certainly can. I just did a quick search on smart bin pricing, and you will find that the range of price from $179 to $49,500 just on that first search. So it's a case of saying, if we've got this range of prices, then look at the feature set, and by the number of features or the complexity of the features, fit them somewhere in that spectrum, and just state that this is what we think would be the prices. Okay, because that's commercially sensitive. You won't always find it. And again, if we go to that really tightly controlled market of medical instruments, if you try and find out how much a piece of medical equipment costs, unless you are a registered hospital, they will not tell you. Because they know they're not going to sell it to you, so you want it for some other reason. So therefore, they're not going to tell you what the price is. So it's not unusual. We just have to make a best guess. And justifying that estimation that you come up with is the key factor.
All right. I just have another question about the prototyping itself. Like I had some 3D design of the product I did just to try. Like I will send an email about just if I can get help in the mechanism itself of the smart bin movement. Like what kind of motors I should use? Should I use a step motor or DC motor? And how to use the gears to make the discs move in the way that I'm imagining that it should.
Yeah, well, we'll help where we can. If we can't help, I'll grab one of our mechanical engineering friends to step in. But for a prototype, we should be okay. So just email us and we can set up a time to have a chat.
All right. Thank you.
No problem. Any further questions?
I think Khaled, you had a question as well. You had your hand up.
Yeah. I think. Oh, okay. Sorry, we are running out of time. I think, but I have a question related to the sensors and the implementation of the system. Should we apply the system in like a hardware, or we can use like Tinkercad, some softwares like that? I do remember that in Cisco, we had a web page in the security course. We had a web page on Cisco's application that we can access as a dashboard to control the IoT devices. In that course, in the IoT security course. So can we do a similar implementation of our project on that program? Like deploying a web page on Cisco.
Ian, he's working with Amina on the sanitizer station.
Yep. If you want to use a simulator or emulator, that's perfectly okay. We understand in many cases either the parts are too expensive or they're not going to be available within the time span that we've got. So there's some very good simulators out there. If you're looking at the connectivity, Packet Tracer is particularly good. If you're looking at geolocation, he's got a mental blank again. Thingsboard is also very good.
Thingsboard, yeah.
But there's a whole variety of those. Yes, use them. No harm in using them at all.
Okay. So we were thinking about trying the particle electron that you can insert a SIM card with it in it, so you can connect to the internet. It's a particle electron and particle photon. It's a similar single single computer board to the Arduino is similar
The
control.
particle, yeah.
Yeah. Okay. The problem is the particle electron we've got that only works in Australia. So it was my bad to order the one. So we are going back to the Arduino. Maybe we can use the Raspberry Pi to connect the internet to the internet. And that
Raspberry
situation.
Pi, if you're not looking for too much processing power, the Raspberry Pi Zero is a very, very good solution. It's very cheap, readily available, runs a full Linux distribution.
I have the 0W. I have it.
That's a good one.
Yeah, we can work on that one if it's okay. Yeah. Okay.
It's tuned for Python, so the Python course would have also helped.
Okay. I do remember that I've tried to install Linux, Apache, and LAMP, Apache, MySQL, and PHP on the Raspberry Pi. That worked just fine. I was wondering about the Cisco. Can we install such thing on the Cisco application?
The packet tracer one, yep. You should still have access. If not, yep, just shoot me an email if you haven't got access, and I'll put you into the packet tracer course again, and that'll allow you to activate it if it's expired.
All right. So it's just for simulation purposes, so we can do the packet tracer. And all right, thank you.
And that goes for any of the courses. If you want access to one of the past courses, just let us know and we'll put you back in. So that's the networking, Python, cybersecurity.
That sounds great. Really, thank you.
Also got C if you want to.
Okay.
In that case, we shall sign off and speak to you all again soon. Remember, if we've mentioned you should catch up with us offline, please do so. We shall be awaiting your emails. Thanks, everyone.
Thank you.
Have a good night, good morning, good afternoon, whatever it happens to be.